Hi, this video covers the entire binary search tree removal algorithm. The previous video focused on just one part of that, which is removing one particular node out of the tree and dealing with pointers pointing at that node. This video covers the entire process of taking a key that needs to be removed from the tree and getting that pair out of the tree, including that remove node part from the previous video, but some other steps as well. This is the operation that we're trying to implement in this video. Binary search tree erase given a key. Remember the previous video covered removing a node pointer. You had to have a node pointer in hand to remove. Now what we're trying to do is make a public function where you give it a key, a k, in our template class, and get that key out of the entire binary search tree. This corresponds to the erase operation in the map abstract data type. You're given a key, you want to take it out of the map. So if the tree does not contain that key, we can't do anything, and we return false. But otherwise, if the tree does contain the key, we can do something, and we remove the pair containing that key out of the tree and return true so that the caller can tell that something actually occurred. Again, this is kind of like the insert operation. There's this rather powerful and complicated public operation that has a bunch of if-then kind of logic in it, and it would be overwhelming to do that all in one big function. It would be humongous and hard to understand. So we are going to factor this into some smaller and more manageable steps. We're going to have an overall erase function that calls some helper functions, and actually those will call some helper functions. Removal is a little more complicated than insertion, so there's more subroutines involved in the removal algorithm than there was in the insertion algorithm. So here's the public erase operation. First thing we deal with is the logic of whether the key is in the tree or not. So if the tree does not contain the key, return false and end the function call. And we're using the contains helper function again, just to not repeat that logic. If we get past that if, that means the tree definitely does contain that key. We call an erase node helper function given the key. And that erase node will do all the work of taking that key out of the tree. Erase node will again assume that the key definitely is in the tree, just to simplify how erase node works. And we do a size minus minus to keep the size synchronized and return true to say that yes, we did change the tree just now. So that's the highest level, top level erase function that's public in the binary search tree class. So this is erase again. Now let's, we already know how contains works and the other stuff is pretty rudimentary, but the thing we need to explain is erase node. So now let's look at how erase node works. What erase node does is it's given a key and it erases the node that contains that key out of the tree. This is a private helper function. It's not meant to be called publicly. For one thing, erase node does not update the sizes, so if a user of our binary search tree class called erase node, their size would get all out of sync, and that would be a problem. The erase node operation assumes that the key is present, so the erase algorithm is responsible for deciding whether the key is present or not, and erase node shall only be called on a key that is certainly in the tree. That simplifies erase node because erase node doesn't have to think about that particular issue. Erase node, it's not responsible for the size or the true false return value. That is the job of the erase function. So now let's get into erase node. Here's what it does. First, finds the node containing the key. This is the node that needs to be removed out of the tree. Remove that node. We went into some detail in the previous video, this step, number 2 here, of once you found the node pointer to remove, how you actually remove it and update the surrounding pointers. So this one we could actually write as a one-liner calling 2 helper functions. Erase node given a key calls find node on key. This is a helper function that would do the normal search of starting at the root and working its way down with left and right child pointers until it finds the node containing key. This find node can assume that there really is that key in the tree. It doesn't have to worry about a missing key, and returns a pointer to that node. I'm not going to show this pseudocode in this video because it's pretty straightforward. We've done a lot of these searches already. There is an implementation of this in the code video that's a little later. So find node returns a pointer to the node that needs to be removed, and then we call the remove node operation, and remove node is responsible for taking that node out and updating all of the root pointer, child pointer or parent pointers that might point to that node. And we covered that in detail in the previous video. Let's just kind of review what remove node does. So there's three cases. U is the node that we're trying to remove. If U has 0 children, meaning that U is a leaf, then we just replace the hole left by removing U out of the tree with a null pointer. And if U has only 1 child, then we replace the position of U with the one and only child of U. And then if U has 2 children, things are a little bit more complicated. We replace U with the in-order successor of U. The way that remove node will actually work in our pseudocode is there's a helper function called remove 0 or 1 child. This is also called splice. In the Open Data Structures textbook, they call it slice, but I'm calling it remove 0 or 1 child. What remove 0 or 1 child does is removes a node U where U definitely has 0 or 1 child pointers. So U is not allowed to have 2 children. And so remove node decides how to remove node U, which might involve calling this function. So if U has 0 or 1 child, we just make one function call to remove 0 or 1 child, and we're done. Otherwise, we have to deal with this successor thing. So let U or let W be the in-order successor of U. We find the successor of W, and then U's pair equals W's pair. So we copy the contents of the successor W into U, the node that we want to get out of the tree. And then we can call remove 0 or 1 child on W, the successor. Remember that a successor node, by definition, has no left child. Therefore, a successor node always has 0 or 1 child. So this remove 0 or 1 child function can handle this for us. The reason we created this remove 0 or 1 child operation is because remove node needs to do that operation of removing a node that certainly has 0 or 1 children, but there's 2 times it might need to do it. So rather than copy pasting that code, we factor that out into its own helper function. So finally, to have a well-defined algorithm, we have to say what remove 0 or 1 child does. So we let S be a pointer to the node that will take U's place. In other words, the surrogate for U that will fill the hole that U left. And that's in the case when U is an only child or null. So we work that out. We know that U has 0 or 1 children, so this S is either a null pointer if 0 has no children, or S is a pointer to the 1 child of U if U has 1 child. We have to deal with the root pointer, so if U is equal to the root, then we're removing the root of the tree, so the root gets reassigned to point to S, and S's parent is null because S has no parent anymore. Otherwise, meaning U is not the root, so U is a child of some other node, then we let P be U's parent. P is the parent of U, and we need to update P's child pointer. So we move P's child pointer, the left or the right, whichever one points at U, to point at this S instead of U. So S is the node taking the place of U, it's filling the hole. So one of P's child pointers needs to be moved to point at that S. And then S's parent is now P. So S used to have U as a parent, but we want S's parent pointer to skip over U and go directly to this P. All right, so what we just did there was kind of a top-down definition of these operations, starting with the public function, working our way down. Let's just look at the pseudocode all in one place to see how this goes together. So this is the public erase operation. It's given a key to remove, and if the tree does not contain the given key, this should say key, then we return false, and that's the end of the erase operation. Otherwise, we know that the key is in the tree, and we call an erase node private helper function that does the job of taking a known present key out of the tree. Erase does size minus minus, so the size is in sync, and we return true. Okay, so what we've handled there is deciding what value to return from erase and deciding whether we actually need to delete anything or not. Now we don't have to worry about those concerns anymore, and we can focus just on removing a node we know is present in the tree. That's what erase node does. So the next function call would be erase node. Erase node just calls 2 helper functions. Find node locates that node. So we've got a key. We have to do that whole thing of starting at the root and going left and right and left and right until we find the node object that contains that key. That's what find node does. And then we call remove node on that node pointer. Remove node does the work of taking a pointer to a node and getting that node out of the tree. So now let's look at remove node. We're kind of drilling down one step at a time here. So now I've got that text described in pseudocode. So remove node is given a pointer u. U is a node that we want to take out of the tree. And here we're deciding if u has 0 or 1 children or not. So if u's left pointer is null or u's right pointer is null, that means that one or both child pointers are null. If one or two child pointers are null, then the number of children is 0 or 1, right? Because at least one of the child pointers is not a child. So if either of those child pointers is null, then we call our remove 0 or 1 child function on u. That will do the work of taking the node u out, given the assumption that u has less than 2 children. Otherwise, u has 2 children. The only way to get past this if is if left is not null and u is not null. U's right is not null. So if we get down here, we know that u has 2 children. We have to find the successor of u. So this here is the pseudocode to find the successor of u. W starts out at u's right pointer, and then as long as we can follow a left pointer, we do so. So while w left is not null, w equals w left. At the end of this while loop, w points at the in-order successor of u. And then we say u's contents is a copy of w's contents. So we copy the key value pair out of the successor w into the node u. For a brief moment here, there are 2 copies of that key value pair, but this has the effect of destroying the key value pair that was in u. So the key value pair that was in u has been overwritten. It's not in the tree anymore. We're almost done. The one last detail is that in this case, we've got 2 copies of the successor's key value, and we need to delete the one that's in the leaf node at the bottom of the tree. We use our remove 0 or 1 child function to do that, passing w. It's not u here, it's w. So the successor node needs to be deleted out of the tree. By definition, you can see here that w is a successor, so it does not have a left child pointer. This loop keeps going as long as w does have a non-null left child pointer. So when the loop terminates, we know that w's left child pointer is certainly null, so therefore w definitely has 0 or 1 children, and the remove 0 or 1 child helper function can delete w out of the tree. So the last thing we need to go over is how remove 0 or 1 child works. It's given a node u that points to a node that for sure has less than 2 children, and remove 0 or 1 child needs to take that node out of the tree and update any pointers that might point to it. So that's the root pointer, parent pointer, left or right child pointers. So if u's left is not null, then s is u's left, otherwise s is u's right. So what this is doing here is figuring out the node pointer s that will take the place of u. So basically we're saying which of the 2 children is non-null. So if u's left pointer is not null, it points to an actual node, then we're going to replace u with the left pointer. Otherwise, so if the left pointer was null, then s will be the right pointer. And there's 2 ways that could go. If u has only 1 child, then in this case s points at that 1 child. U right is the 1 non-null child pointer. The other way this if statement could work out is if both children are null, because u has 0 children, then s would be u's right pointer, which is null, so then s is null. So this if statement works correctly. It figures out what pointer should take the place of u. That'll either be the one and only child of u, or if u has no children, then s is assigned to null. Now we decide if we need to update the root pointer or a parent node's child pointer. It's one or the other. So if u is currently the tree's root, then we need to update the root pointer, and we know u has no parent to deal with. So we say, if that's the case, then the tree's root is now pointing at s. S is the pointer that's taking the place of u, and p is null. P is going to be a pointer to the parent of u that we use down at the end of this function. Otherwise, that means u is not the current root, which is another way of saying u has a parent for sure. So p is u's parent. P is the parent of u. And if now we have to update the child pointer of p, and we have to decide which one it is. So if p's left pointer is equal to u, then that means u was the left child of p, and we say p's left becomes s. S is the node pointer that's taking the place of u. Otherwise, we know that P's right pointer has to be equal to U, so we set P's right pointer equal to S. So now we've replaced the left or right pointer that needs to point to S instead of pointing at U. And the last step is if S is not null, then S's parent is P. So it's possible that S was pointing at null, but if S is not null, then it's a node and it has a parent pointer. We need to update that parent pointer to point to the right place. So S's parent points at P. Whatever the new parent we worked out of S gets assigned on that step. Okay, so that's it for the entire deletion process.